In this work, we present a learning-based document enhancement algorithm to remove photometric distortions to get a scanner quality document image. The visual quality of document images captured by phone cameras is usually inferior to images captured by scanners. The problems may be caused by different reasons, such as distortions due to paper deformation or distortions due to uncontrolled lighting environments. Here are examples of document images captured by real cameras. Each image often has multiple photometric distortions, including shadows, non-uniform shading, and color shifts. We propose a comprehensive method using our network to generate shadow-free and scanner-quality document image. Existing document enhancement algorithms have their limitations. Some methods usually focus on only a small subset of those complex distortions, such as removing shadows or correcting shading. Addressing only one distortion may result in a suboptimal solution. Also, the effects of eliminating shadows and shading are limited. Here is an example. Some of the previous methods will remain shadow artifacts in their results, especially when it deals with complex shadows. In contrast, the proposed method generates well-illuminated document images, which perform better shadow removal ability than previous methods. The proposed method can further get scanner quality document images, which result in better legibility and perceptual quality. We will provide more visual comparisons with previous works in the later section. Our data synthesis process can be shown in this figure. First, we use CWMS to model the shapes of shadows cast by occluders. There are three sources for simulating shadow maps: CWM maps, large-scale soft maps, and Perlin shadow maps. Besides, we use gradient maps to synthesize shading maps. Second, in order to enrich the dataset, we use different transformations to add the shape variations. Third, we add color variation. We sample color in a given range and use them to obtain synthesized shadow maps and shading maps. Finally, we got triplets for our synthesized dataset for training. We collected document images and silhouette maps from different open datasets. There is a wide variety of documents content in them, including papers, receipts, textbooks, notes, and magazines. All of them are well illuminated with clean and sharp content. Based on this process, we generate 7,000 triplets for training our network, 1,000 for validation, and 2,000 for testing. We call our dataset Synthetic Scanner Quality Dataset, or SSQD. Here are 4 examples from our SSQD. With the synthesis process, we can generate various illumination conditions in a fast and flexible way. We consider the different characteristics of shadows and shading to devise our model architecture. At the first stage, our deshadow net runs to eliminate shadows. We use the attention mechanism to extract the long-range dependencies within an image. Unlike BDSRNet, which employs an external module GradCAM to extract the attention map, we apply the self-attention mechanisms proposed by CBAM, inspired by the NPRNet, which use self-attention to restore degraded images. We have designed our network with an encoder-decoder architecture built with channel attention blocks to refine features as they propagate. The shading net predicts the estimated scanner quality image and the estimated shading map. We encode the global information of shadow-free images upon the UNet architecture by adding 2 downsample layers and concatenating the outputs with the encoder layers. The encoded global information helps preserve content and improve visual quality. Our proposed model progressively learns the destroy function for the degraded inputs, which is more stable to train when the trained problem is decomposed into 2 subproblems, and supervisory signals are provided to each of manageable steps. Here are our loss functions. The proposed method is evaluated on real-world images in terms of shadow removal and scanner quality. BDSRNet and RDShadowNet produce the most robust DShadow results across different datasets. While BDSRNet achieves comparable performance with our method, RDShadowNet has a significantly smaller model size than theirs and is therefore more suitable for mobile devices. One of our contributions is the data synthesis procedure that enriches the training dataset variations. Across all test datasets, models trained using SSQD generally perform significantly better than those trained using SDSRD. This shows that our SSQD is not only more effective but also agnostic to deep learning models. The table shows such comparisons using the testing sets of our SSQD. Our method achieves the best SSIMP and PSNR scores. We also conduct experiments in terms of OCR performance to validate the legibility of document images.